Hey there, everybody. Welcome to another Chem Complete episode. I am Professor Tomney, and we are going to continue our lectures on enolate chemistry here. And in this lecture, I want to focus on Claisen condensations. So that is coming up on the channel right now. Okay, thank you for joining us, and let's get right into it. So, Claisen condensations are going to involve the use of esters. So this is going to differ from aldols, where we were primarily using aldehydes and ketones. So we will be utilizing esters as the main source or focus of enolates here. Now, I'll, as usual, start with a relatively simple example. So let's use this as our ester. It's about as simple as they come. Now, there's a couple of other things besides just the fact that we're using esters that are going to change here. And one of the biggest changes that we are going to see when we do Claisen condensations is the base that is used will usually be some sort of alkoxide ion. And in fact, it's usually going to mimic or mirror whatever ester functionality we see. So if you take a look here, we would have a methoxide. Now, if this CH3 was a CH2 and there was another CH3 after it, it would be an ethoxide. And so we will typically see whatever this little chunk of the ester is as the corresponding base. And so what we will use for our base here is sodium methoxide in order to run the enolate Claisen reaction. Now, a lot of students will ask, why can I not use hydroxide? Right? Because that's what we've been seeing in the aldol condensations. And the answer is that the use of sodium hydroxide with an ester is actually going to create a separate side reaction that you are not looking for here. And that reaction would be saponification. So saponification is the process by which the hydroxide would attack the carbonyl, the OCH3 group would leave, and you would end up through an additional acidic workup making a carboxylic acid and cleaving that ester portionality, and that is not what we're looking to do in the Claisen. And so by using this methoxide ion as the base instead of hydroxide, we're able to avoid any type of saponification reaction or cross reaction that might occur. Okay, and then there is a separate follow-up. We want to do H3O+. Sometimes you might just see it as H2O, but you want something to work up that's going to be at least mildly acidic in order to essentially kill off an additional enolate formation. We'll see why as we start to go through this here. Okay, so let's start. The way I want to kind of break this down, we're going to start with a self-Claisen. Then we can take a look at a mixed Claisen if we would like. And then in a separate lecture, so the one I do after this, we will look at an intramolecular Claisen, which is also known as the Dieckmann reaction. So let's start with self right now. Okay, so for this particular reaction, what we are going to do to start, let's go ahead, and I'm actually, as I'm doing this, let's take this, we're going to make it CH2, and then we're just going to bring one of those hydrogens up here for the sake of the mechanism, all right? So, the first step, we need to form our enolate. And as usual, we're going to have the base do its thing by removing an alpha hydrogen. And so what that would leave me with is, I've got the CH2 here. That's my enolate portionality in resonance with the carbonyl. And then I still have my OCH3. And as you are getting into condensation reactions, you may also see these written sometimes like this. You might see C double bond O, and then instead of OCH3, it might say OME for O-methyl, or it might say OET for O-ethyl. So if you see that in books or your instructors using it or anything like that, don't get confused. That's just methyl ethyl. It's as these reactions get more cumbersome and they get long and tedious, a lot of times instructors will just start writing OET or OME as they're moving along quickly. Okay, so coming back to the reaction here, we have the enolate. It's going to undergo a self-Claisen. So that means I need another one of my esters here. And similar to an aldol in this step, it's the enolate that's going to come and attack this carbonyl. So I would expect that the lone pair associated with this carbon will come to attack the carbonyl. And this will obviously open up because we don't have carbon with 5 bonds. And from there, you will end up with the new chain, and that carbonyl here will become a tetrahedral intermediate. So I'm kind of drawing this first chunk here in reverse. So I'm going to put the CH3O on this side now. Okay, C double bond O. And then here's the CH2. Okay, so this CH2 is the enolate CH2 that attacked. And then I've got a O minus as that carbonyl opened up. And don't forget what I've still got here. I've got a methyl group on one side, and then the other portion on that carbon was the OCH3. Okay. Now at this point, it also makes this very convenient for wrapping up this reaction. So a lot of students think this is where we need the H3O+, and that's actually not the case. We don't need it until the next step, which again, I'll point out why in a minute here. Okay, so as we're going along, if you take a look at this, OCH3 was really the base, right? If this is Na plus and OCH3 then the major base that was here was OCH3. And so this will very readily leave to replenish that catalyst in reaction. And this carbonyl can come back down in order to form the initial product. So the initial product that I would see coming out of this would be that I have an ester, and then that ester would also have a ketone, okay, like this, and that OCH3 left, so here's the CH3. So this would be the result that I would get from this, and this is known as a beta keto ester. These are the types of products that we form from most Claisen reactions, a beta keto ester. And the term here is coming from, if I look at the ester portionality, which is right here, right? Then if I go here, this is an alpha position and this is a beta position. So when it says beta keto, it's referring to the fact that there's a ketone in the beta position relative to the ester functionality that is left behind here. Now here's the main reason why I need the H3O+. This is the final product right here, okay? But the final product, if you take a look at it, this alpha carbon is extremely acidic compared to the starting material because it's got resonance here and it also has resonance here. So it's got double resonance on either side, and that makes this enolate substantially more likely to form compared to the starting material. And so what you're going to end up with is, if you let this run, you can form or deprotonate this right here. It forms pretty acidic enolate. And so the H3O+ is to reprotonate or kill that effect off, okay? So again, the H3O+ is really just added here as a second precautionary step, because what would happen is that once you have released your O-methoxide, right, that OCH3 could very readily come back in and start forming enolates here. And so how do you kill that off? Well, you add acid in to that base, and those two can react with one another and preserve the beta keto ester that you are looking to form. Okay, so that is a self-Claisen. Now, you can probably guess a mixed Claisen is along the same lines, but instead of attacking itself, it's going to attack a separate one. So in this particular lecture, I already went through when we did it with the aldol, and I showed that the self-condensation could still be happening. We're going to ignore any products from self-condensation here, and I really just want to focus on the mixed Claisen. So similar to when we did aldol mixed, it is ideal to control for your product, which means, if at all possible, when you are trying to run this, you want to select one of your two esters to be an ester that does not have alpha protons, because then you don't have competition for enolate formation and you don't have this crazy mixture of products. So what would something look like that makes a good mixed Claisen condensation? Well, we can start with our ester that will have the deprotonatable or the enolate potential. Okay, so we'll do what we stuck with before. So here's an ester. We'll utilize that. Plus, we'll go ahead and we'll utilize another ester, but this one is not going to have any alpha carbons that it can work with, or at least no hydrogens on those alpha carbons, I should say. Okay, so here's another one, OCH3, right? So if I take a look at these, only the one on the left has the potential to be turned into an enolate. So it is again methoxide, so I'm going to use NaOCH3, and then I need to add in a secondary step the H3O plus just to try to preserve that product and kill off any excess base that might be sitting around. Okay, so the first step would be that we would form the enolate out of this ester right here, and that enolate is going to go in and attack the other ester that does not have any type of alpha hydrogen for removal. So we've got the aromatic ring. Many students will ask, can I abbreviate this as pH? I always tell my students, yes, you can abbreviate pH for phenyl, but it is always best to ask your instructor how they feel, if they're comfortable with you just writing pH, or if they want you to actually draw out the phenyl ring. And so we've got OCH3, and this enolate right here is going to come in, attack this carbonyl, and that carbonyl will open up. And so what I end up with is, from left to right, the CH3O, C double bond O, okay, CH2. That CH2 attacked a carbonyl. Now this would be O minus at this point, and I would still have the ring, if I can draw it properly. Okay. And then I would also have the ester portionality. Now in this case, this is what I'm going to get rid of, this OCH3, right? And then the ring, I'm sorry, not the ring, the oxygen is going to come back down to form that carbonyl. And so what do I get for the final product? I'm going to take what's here and I'm going to draw it out as the final product. I would get the ester chunk that came from my enolate, and then that would be attached to another carbonyl, and that carbonyl would have a phenyl group as its other chunk or substituent here coming off. Okay, so again, if I take a look at this, this is going to be, because this is a carbon and a carbon on either side, this is a ketone, and this is a beta keto ester, right? Here's the ester portionality. So that would be the full product, the beta keto ester, that would form from this mixed Claisen condensation. And again, we're not going to go through the entire steps or show it, but this could also undergo a self-condensation. So you do potentially have that competition going on there. Okay, so I think that pretty well sums up Claisen reactions. So a general reminder, if you want to support the channel, head on over to chemcomplete.com. We have lots of resources over there. Many of them are free if you sign up for a free account on the website. And I also have some guides that are very useful if you're trying to get through organic chemistry over there. If you would like, you can also support the channel by the new thanks button that YouTube has, which allows you to donate whatever you feel like if you appreciate the content and the video material. And then, as always, you guys know, the best way to support the channel is to continue coming back and using Chem Complete as your main organic chemistry lecture series. I know there's a lot of options out there, and I thank you for continuing to learn with me. So, with all that said, have an excellent rest of your day, and I will see you guys in the next one.